Hello, everyone. I'm glad to be here. My name is Otávio Santana, and today we will talk about Java and Cloud Native with a special guest. But before, please subscribe in our channel. So if you want to know more about Xfix, check out our website, so xfix.io, where you can get several informations. And yes, let's bring this special guest for today. Hello, Josh. How are you?
Good afternoon. How are you? Good
I'm
evening.
fine. Good evening to me. Yes. So I'm glad to stay with you to talk about cloud native. That sounds an amazing topic.
Well, I like it. Yeah, I'm a big fan. It's a topic that changes all the time. So every time I do this talk, there's something new, something exciting to talk about.
Yeah, yes. By the way, read your book about it. That sounds good as well.
Thank you. Thank you. This will be a very different talk than that book, unfortunately, because it has changed so much. It's the problem.
Okay,
Always
don't
change.
worry. So the stage is yours. So go
Okay.
ahead.
Thank you so much. Let me share this screen. Okay, can you all see me? Yeah, it looks like you can.
Yes,
Good.
we can.
All right, good stuff, everybody. Thank you so much. So my name is Josh Long. It's so nice to meet you. I appreciate you being here. Obviously, there's a lot of places that you could be, and you chose to be here with us, and that's great. I just realized I forgot to start my slides. Sometimes I don't even use my slides, and so I forget about them. But this time, I think I'm going to use my slides. So let's just do that here quickly. Cloud Native Java. Okay. So okay, so here we go. So my name is Josh Long. I work on the Spring team. I'm a Spring developer advocate, a Kotlin Google developer expert, and a Java champion. And of course, I am at your service. So if you have questions, comments, feedback, whatever, there's my Twitter, there's my email. Please don't hesitate to reach out to me. My code that we're going to look at is here down on the bottom of the screen on the slide, so you can find that there. And of course, I work for you. I have done lots of training videos that are about different topics, including an older version of Cloud Native Java. I have a book called Cloud Native Java. I have a podcast that I do every Friday where I interview people about different things in the Spring ecosystem. And I have a blog called This Week in Spring. And of course, I have a video series called Spring Tips and a new book called Reactive Spring. And so that's my slides. Those are all of the things that we're going to show in the slides. We're going to talk about Cloud Native Java. Now, Cloud Native Java is not a particular technology. It's more an approach, right? It's more a philosophy. The idea is that when you work with a cloud, you are embracing an environment that will allow you to build software more quickly, more iteratively, more rapidly, right? The goal in a cloud native Java scenario is to get software into production as quickly and often as possible through continuous delivery. When you move to this, when you realize that this is what you want to do, when you realize that going quickly is valuable, because it allows you to make mistakes, to improve your code, to release value for the customer, to respond to changes in the market, and so on. When you realize that that's what you want to do, then a lot of things change, right? When the goal is to iterate, to grow as an organization more quickly, then a lot of things in the technology stack change, right? So we do cloud native Java, not because of a technical concern, but because it's better for the business. It helps the business make more money. It helps you write code that more people want. It makes everybody just a little bit happier. So when you do this, the goal has to be to embrace technologies that give you the ability to iterate quickly, rapidly. And so always, I keep this in the back of my mind whenever I talk to people about software and about Spring and about Kubernetes and all that. I keep it in the back of my mind that the goal here is to give people stuff faster so we can learn from those iterations. So what must change? Well, if you're in a large organization and you have a large code base, it's very hard to release that code base, that large code base, quickly, because you have to wait for everybody that's working on the code to integrate and stabilize their code. This is a problem. And so the first thing that people look to do, of course, is in the programming area, at least, the first thing they look to do is to reduce the size of the code base. Obviously, there's other things you should do. It's not just about the programming. Obviously, there's things like DevOps and continuous integration and test-driven development and Agile, all these things are all about increasing the speed at which we can iterate. But when it comes to programming, one thing that you can do is to reduce the size of the code base, to make it smaller. The smaller the code base, the fewer the people working on it, the less change, the less interactivity required, right? The less integration, the less stabilization of the code that is required. And so people look at their large code bases and they say, how do I break this up? How do I break it into small pieces? They look for logical places to break the code base into small chunks. And they find something like an aggregate or a bounded context. And they use that as a way to extract out parts of the domain model into a separate thing, into a separate code base. But remember, what we want is the ability to move quickly. We can't be waiting for everybody in the organization to finish their code before we can deploy our code. So it's not okay to just extract it out into a separate code base and then wait for everybody to stabilize so you can put it inside of a big giant monolithic .ir file or something like that. That doesn't work. So instead, people move to something like microservices. Microservices are small network services that have a small bounded context or a small domain and that communicate over the network. The benefit of this is that I can deploy this microservice without having to redeploy the code for this other service over here. This is very useful, right? I get independence, I get agility. But of course, when you do this, you are now building a distributed system. And that distributed system has problems, right? Building a distributed system brings complexity, and that complexity is hard to meet if you're not prepared. So today, my friends, we're going to talk about how to meet that complexity with Spring. And there's several things that we're going to talk about. We're going to talk about, of course, how Spring better integrates with Kubernetes. We're going to talk about how Spring supports reactive programming. And reactive programming, I think, is kind of interesting in of itself. I've done whole talks about reactive programming. But basically, the big thing here is that reactive programming gives us three big benefits. One is that it makes it so that we can write code in such a way that we're never wasting threads, right? Right now, before Project Loom, threads are very expensive. They're very few. They're hard to create more of. It's not easy to create more of them. So Project Loom will fix that. It'll make it so that they're much cheaper. That's part one, right? That's the first thing that we care about. For now, though, for a lot of us, that's just not the case. We need something where we can write code in a way that we are not sitting on a thread, keeping the thread, right? Because that thread could be helping somebody else. And if you look at a lot of the things that we do that occupy space in a thread, or time rather, in a thread, there's a couple of things that are obvious. One is CPU-bound work, algorithmic work, Bitcoin mining, running Slack, the Fibonacci series, right? Cryptography of any kind. This stuff is CPU bound. It takes time to compute a result, and there's nothing you can really do about that, right? That's what the CPU is for, is to do this kind of stuff. So that's one thing that you can do on a thread that will take time on the thread, and that kind of makes sense. Yeah, you can't avoid that really. The other thing that people do today that shouldn't be on a thread, but for some reason is input and output. Input and output involves reading data and then waiting. And so right now, the code that we use, most of us use Java IO input stream and output stream. Java IO input stream is an interface that allows us to read data from a stream, and then we must wait for that stream. We just sit there waiting. That input stream hasn't got data for us immediately. We need to wait for it, and that's the problem. If we could ask for the data and then move on, then we can jump off the thread and give the thread back to the runtime. Then something else in the system that needs that thread can use it, and then when the data is finally here, then we can start processing it, right? So this is an asynchronous approach to doing input and output. Java NIO supports this. Java NIO is very painful to use for any kind of serious work, though. So people tend to use something like Netty. Netty is something that builds on top of it. But then you need to have a programming model, right? You have to have a programming model that lets you write database access, network services, message queues, web services, all these things. There needs to be a programming model that uses this asynchronous I/O approach. And that's where reactive programming can help you. It gives you a programming model that lets you write code that avoids wasting time, especially with I/O on a thread. That's the first thing. The second thing that you get when you use reactive programming is you get ease of composition. So it becomes much easier to take data from this reactive stream and this reactive stream and this stream and this stream and this stream and put them together and to compose them into one big stream or to change them in some way, because they're all the same thing. Think about what you're dealing with right now in the non-reactive world. The non-reactive world is full of different APIs that don't agree with each other, right? Because there's no core type in the JDK, or rather, there has not been a core type in the JDK to support this. So for example, suppose you want to read 8 records from a REST API, and you want to read that into memory. Well, that's just 8 records. Let's say it's very quick, instant. Okay, so you can use a collection for that, no problem. What if you want to read an infinite stream of data? Like it's just telemetry data that will be created every, it won't stop. It'll just keep streaming forever and ever and ever. Maybe you can use a Java 8 stream for that. What if you want to get data from Kafka, right? You want to get messages from Kafka, and that data might come, at random times, and there might be an infinite amount of it, or there might be just 100 records. We don't know, right? Well, what's the API for that? Well, then you use the Kafka API. What about RabbitMQ? What about JMS? What about WebSockets? What about service and event streams? What about data coming in from a network socket? Do you see the problem here? All these things are different kinds of APIs, and they all have different ways of saying, here's some data, process it, right? And so a lot of what we do when we write code today in 2021 is adapt or connect one API to another because they don't understand each other. And this makes our code full of boilerplate. It's a nightmare, right? It's just boring, dumb code. And so reactive programming solves that by giving you one type. So if you want to get a stream of data that is going to be very quick and have lots of data, or maybe even infinite data from Kafka, you use a reactive stream. If you want to get just 2 records from a database, you use a reactive stream. If you want to get WebSocket data, you use a reactive stream. It's the same thing. And because it's the same thing, and because there are operators like the Java 8 Streams API, it's very easy to do things in a reliable, consistent way for all those different streams. This gets us to the third point, which is that reactive streams give us a lot of consistent operators that make it easier to build reliable, safe code. Things like map and flat map and retry and timeout and on error resume. These give us the operators that we need to build safe code. So when we talk about Kubernetes, you don't have to use reactive programming, but I cannot imagine writing software in 2021 without reactive programming. If you start a new project today and you can use reactive programming, but you don't use reactive programming, you're burning money. There's no point to it. It's not harder, it's not more difficult. It's just you're burning money. You don't seem to care about spending money for no reason. So I think you should start with reactive programming unless there's a very specific reason. And there might be some API that isn't, that just doesn't support reactive programming. But as you'll see, I think 90% of what you're going to need to do today is already well supported in the reactive world, if not more, right? Maybe 100%. So let's go ahead and try it out. We're going to build a new service. We're going to go to my second favorite place on the internet. My first favorite place, of course, is production. I love production. You should love production. You should go as early and often as possible. Bring the kids, bring the family. The weather is amazing. It's the happiest place on earth. What I'm going to do is I'm going to bring in the reactive web support. I'm going to bring in Lombok. I'm going to bring in Spring Native. I'm going to bring in the actuator. I'm going to bring in H2, which is an in-memory SQL database. And I'm going to bring in customers. I'm going to call this service customers. And I'm going to just use this version of Java, this version of Maven. You don't have to use Java, of course. Obviously, we have good support for Kotlin or Java or Groovy or whatever. And then you have the choice of what version you want to use, right? Java 16, 11, and 8. Obviously, 8 is a terrible choice in 2021. It's old, it's slow, it has less security, less features, less robustness, less readiness for production. Java 11 is the current long-term supported version of Java. It's also the version that is most natural for people to use when they're using GraalVM. And there's Java 16, which is the current supported version of Java. And that'll be the old version of Java pretty soon when Java 17 comes out. So for now, I tend to just use Java 11 or 16. They are both technically superior to Java 8 in every way. They're also morally superior to Java 8 in every way. You will not like the look of sadness and frustration on your children's eyes when you tell them that you're using Java 8 in production. Don't do it. Be the change you want to see in the world. Do the right thing. Use Java 11. So I'm going to go ahead and hit generate, and that'll give me a new project. And I'm going to open this up in my IDE. Okay, so we have a new application. Oh, Kotlin. Okay, whatever. We'll just leave it in Kotlin. I must have forgotten to take it back to Java. So we're going to build a new application that talks to a database. And here, I'm using R2DBC. R2DBC is a reactive relational database connectivity abstraction. It's a way for people to talk to SQL databases. And there are different drivers that you can use. Did I add R2DBC? No, I don't think I did. No. Okay, wait. Kotlin, Reactive, Web, Actuator, Native, R2DBC, H2. There we go. So I'm going to copy and paste this into here. Maven. So R2DBC is a reactive relational database connectivity abstraction. Spring has we have great support for the native reactive MongoDB, Cassandra, Couchbase, Redis, Neo4j drivers, all these, and many more, including Google Cloud Spanner and a bunch of others, Azure Cosmos DB. They all support reactive programming. But we realized that there's not a good story for people to do reactive SQL-based data access. And so we created this thing called R2DBC. R2DBC is a SQL data access layer. We could not use JDBC because it's blocking. It's not reactive. So we created R2DBC. And there are drivers for H2, for Postgres, for MySQL, for MariaDB, for SQL Server, for Oracle, for SAP, for, just it goes on. The list is endless, right? It's just an did I mention H2? I mean, they're all here, right? So lots of different options. And so what we're going to do is we're going to write data that talks to a SQL database. I'm going to describe this using a record. This is kind of like a Java 15 record, right? And a record is it's a class that has a constructor and it has a read-only field. This is a val, not a var. So var is mutable, val is immutable. And then I want to create a Spring Data repository, right? So I need to annotate this with @ID, so it knows that this is the primary key. And I need to create a repository, customer repository. This is going to extend the reactive CRUD repository inside of Spring Data. And that CRUD repository provides methods that do data management. So save, find, count, delete, etc. Okay? And so I want to build then some sample data into the database. So I'll say class Initializr, application runner, okay, at component. And this is just a Spring Bean that when the application starts up will be invoked, and I'll inject a reference to the repository here. And what I'm going to do is I'm going to write some data to the database so that we have something to work with. So val names equals, and we're going to create a reactive stream of names of people on the Spring team. So you can see this is a reactive stream of names. Names like Madura, Dr. Sayer, Olga, Violetta, Spencer, Yushin. Who else do we have? Let's see. That's 7 right there, and we need one more name, Stefan. Okay. Well, so there we are. There's our names. And now for each one of those, I want to take it and I want to turn it into a new customer. So I could describe the implicit parameter here like this. I could say create a new customer, and I will pass in the name. And the name is there, but this will be nullable. So this ID needs to be nullable and mutable. All right, so there we go. Good. So now I have a customer, and the result is I have now a stream of customers. And then I'm going to take each one of those, and I'm going to write it to the database using the reactive stream. One thing that you will note in Kotlin is that for lambdas that have just one parameter, you can just drop this and use it. Okay, it's very convenient. The next thing I want to do is I want to write that to the database. So I'll say saved, and I'll say customers dot. And here I could use map. Map would work, except that the result of this would actually be a publisher of mono of customer. Right? I don't want that. That would be a problem because now I have let's see, map to repository save. Right? If I do that, what I get is a reactive stream of customer. I don't want two reactive streams. I just want one. So I want to unpack it, and the way you do that is you flatten the rights, right? So flat map, okay? Flat map. Okay, so there's my my names. There's the data. Now, if I run this code, nothing will happen. And the reason that nothing happens is because I have defined a pipeline through which water will flow, but I haven't turned on the faucet. In order to do that, you have to do saved, not subscribe, right? The problem is that subscription is async. So if I do this, 1 and then 2, there's no guarantee that the saving of the data will happen before 2. You might see 2, and then then in the database you'll see all the data being written, right? Because this is asynchronous. So in order to force one thing to happen before the other, you need to use operators. So we will use the operators, and that's very important because I have some other things that we need to do first. So this is data, right? Let's do the DDL. So here, I'm going to use the database client. I'm going to inject that as well. I'll say inject this. Private val DBC, database client. This is the reactive database client, like the JDBC template. And here I'll say this .dbc.sql, and of course, create table, customers, ID, serial, primary key, name, var, car, 255, not null. And by the way, you know what? One of the things that just happened, my friends, I wonder if this will work. We can try this right now together. I haven't actually tried this yet. In the reactive world now, you can do this. See if that works. That should work, right? That's much better. Okay, so let's try it. So actually, maybe I don't need this. Maybe I can leave that off. We'll try it right now, okay? So that's the one thing I wanted to do. But the other thing I wanted to do is I want to get all the data and just visit all the records. So I'll say repository.find all. Okay. So I want the save, and then and only then I want this. So I say saved.then many all.subscribe, and here I'm going to print line each record. Okay. So let's see here. It's going to run this. Okay, did it work? What happened? Table customer. Okay, so the schema is customers. Okay, there we go. There's our data. It's worked. Congratulations, right? So now we have the data in the database. Are we done? Of course not. I think we need a REST API maybe. So one way to do that is just to create a REST controller, class customer REST controller, and we'll just inject the repository here. So customer repository, and I'll create an endpoint called customers, and it'll be fun, get equals this dot repo.find all. And now we can restart this again. Okay. So localhost customers, there's our data, it worked. So now we have the data in the database. Are we done? Can we go to production? Of course not. There's things that we need to do. And one of the things that we need to do is to support observability. One way we can do that is with the Spring Boot actuator. That's this module right here. It's a set of managed HTTP endpoints that give you information about the state of the service. So I can say, I want to expose all the endpoints. I can say show all of them. I want to show the health details, right? Show details always. And then I want to also enable the Kubernetes probes. Okay. Now this Kubernetes probe, you might want that to only be available in Kubernetes, and you can do that. You can actually put a profile. You can say activate on cloud platform Kubernetes. So all the configuration after this will only be activated if you're inside of Kubernetes. This will be activated no matter what, right? For example. And so this is very useful. You can actually say, okay, well, maybe I want server port equals 8080. The other thing that you can do is you can import configuration, right? So I can import configuration from a class path or from the file or from a config tree. Now, you can take, in Kubernetes, you can take something called a config map. It's a directory, it's a dictionary of keys and values, and you can mount it as either a volume on your file system, in your pod, or as environment variables. If you mount it as a volume in your pod, what you will get is a directory structure like this. So let's say I go to here, cd config, and you will have, for each key in the config map, you'll have a file, and for each value, you'll have, let's say we want to have 8010. Okay, so cat server.port. The file has, the property is called server.port, the value is called 8010. So that's what's inside my file. So now I'm going to import that. I'm going to say, okay, import home desktop config. Okay, you don't forget this trailing thing here. So that's going to import the configuration from that config tree that you would get if you mounted a config map as a volume in your pod. Now, I have, let's see, so server.port will be 8080. I put it to 8010 in the config map here, right? So I'm going to restart the application. I want my application to think it's running inside of Kubernetes. If we're actually running inside of a pod, this will automatically be true. This activation criteria, this predicate, will be true. But you can say that you can force your application to think it's running inside of a particular environment, even on your local machine, by providing program arguments like this. So I can say Spring main cloud platform equals Kubernetes. So here I'm overriding the default value that you would get automatically otherwise. And so now I'm forcing it to think that this is true. And because it's thinking that's true, it's also going to import this. And so it'll get the configuration that overrides that, right? So let's see. There we are. It says port 8010, right? Even though we have 8080 here, it's getting the configuration from outside in the config map directory. So that's very convenient. We have the configuration here, etc. Okay. Let's check out what else we get. Okay. So we have now here an actuator. Sorry, 8010. There's the actuator, and the actuator gives us a set of HTTP endpoints, like for example, what beans we have and how they're related to each other, the health of the different components in the application, including the database, the connection factory for the database, the file system, and things like that. You also have two very convenient things: liveness and readiness. These are probes for Kubernetes. You put these in your pod. You configure. Readiness. You configure this in your pod, and you tell your pod to check the readiness probe to determine if the service is ready to be put into production, and you check the liveness probe to determine if the service is still healthy and able to continue to serve in production. We configure this stuff for you automatically, but of course you can change things, right? So, for example, let's say I wanted to create another REST controller here, class availability REST controller, private val. Application context, AC, application context. Okay, and I'm going to use post mapping down. Okay, run down, and all I'm going to do is when somebody calls this endpoint, I am going to provide I'm going to publish an application context event. So I'll say availability change event, publish this.ac. I'm going to say availability, so I'm going to say liveness change event, liveness state broken. Okay. So what that's doing is it's going to publish an event to force the liveness probe to say that things are bad. Okay. So this is gone. Let's restart this one. Okay. So now you can see this says liveness is here. It says it's up. Now we go here, curl -x post HTTP localhost 8010 down. Now it does down, right? So you can publish events to trigger whether that should go down or not. And when you do that, the application will then get an event, right? You'll actually have an event, and the application, the container orchestrator, in this case Kubernetes, will ask, hey, is that service still healthy? If it's not, we need to shut it down. And the question then is, how do you shut it down, right? By default, you have immediate shutdown, like this. But you can also do graceful shutdown. Graceful shutdown is where you wait a little while. So the amount that you wait is configurable. You have to specify it in both Kubernetes and your Spring Boot application. But I can shut it down gracefully, and then I can wait 30 seconds, that kind of thing, okay? So you shut it down, you wait 30 seconds, and what happens is Spring Boot stops accepting new requests. It'll let you finish the existing work and then allow you to shut down so you can finish any existing transactions so they don't get killed immediately. When the container orchestrator, Kubernetes, tries to stop your pod, it'll send a SIG term and then a SIG kill. If you use graceful shutdown, that SIG term comes 30 seconds before the SIG kill. So we have this configured here. We have our health endpoint. We have other endpoints as well, though. So, for example, the info endpoint is where you can put info that helps you identify your application. So I could put info.id equals, or info.message equals hello world, right? You can also put information about the Git version of the application. So plugin group ID, Git. Sorry, let me do artifact ID.
Hey Josh, there is one question from the audience.
Yeah.
Luca Lopes did a question. You'd be good practice if you string data from Webflux with Kafka as data REST service to do a lot of data.
Is it good practice to use Webflux with Kafka and Webflux?
Yes.
Yeah. Oh, yeah. This is great for data. If you have a lot of data, this is the best thing you can do because you'll be able to scale a lot more. You can handle many, many more requests. That's the goal, right? Is to handle many more requests at the same time. It's each single request, maybe it's a little tiny bit slower, right? One request is slower than in the old synchronous imperative blocking IO because you might have movement from one thread to another, but you can handle many more requests, right? So it's much better. You have better scalability. You don't need to buy as much data center capacity. Reactive programming is all about the scale. It's all about handling more with less hardware. Okay, so great question. This is the Git commit ID plugin. This plugin will actually build out information about the application. It'll give you information about whether the service, about how the service was initialized. So git init, git add, git status, git add, git ignore, git add .maven, git commit -m. Okay, so now I've got my Git repository. I'm going to do maven tests clean package. Okay. Okay, so it's just going to build everything, and you can see that when it builds it, it gives me a file called git.properties, and this has the git build username, the tag, the commit ID, the message, all this stuff that you get from the Git repository. Now imagine you have this in a continuous integration environment or a continuous delivery. You do a git commit, git push, then you in your CI environment you build the application. This gets run, it creates all that information, and then that gets shown here. Git main commit ID, and there's my custom message as well. So now when somebody logs into production, they can see, oh, this version of the code came from the CI environment. Here's the version of the code that we are using in production. So if we want to fix it, we can do a git bisect on this particular commit ID. Very useful, right? Okay, so we have a number of different endpoints here. Lots of different endpoints at the actuator. The environment variables, the loggers, the heap dump, thread dump, metrics. Metrics is very useful, gives you keys and values. You can use this with Micrometer, which is a project that we created that helps you do vendor-neutral application metrics. So it's a great application. It's an abstraction, kind of like JDBC or R2DBC, but for databases that do time series information. So Graphite, StatsD, Prometheus, very common in Kubernetes, Wavefront, CloudWatch, Datadog, Dynatrace, all these different ones, Google Cloud Stack Driver, Azure Monitor, all that stuff is supported through this system, right, through this abstraction. And so you can do a lot more than what I've shown you here. We just don't have a lot of time. So now we have all these things. We have observability built in. We looked at configuration. We looked at building our application in such a way that it would support observability. We looked at all these different sort of use cases. Now I want to get this thing into production. And of course, hold on 1 second. Let me make sure everybody's okay. I'm getting a lot of messages here. I want to make sure.
Okay.
You have a question?
Yeah, there's one question from Philip Silvestre.
Yeah.
What's the best approach to use a non-reactive library in a reactive application?
To ensure what?
The best approach to use a non-reactive library in a reactive application.
Oh yeah. Okay. So great question. In reactive programming, you have this thing called a scheduler. So let's see. Where's my initializer? So here I'm subscribing to the data, but I can subscribe on a scheduler. Okay. And so here, for example, I can provide a separate thread pool, and you could use any other thread pool you want, right? Maybe you have a shared one, or you can just use the one that we provide, subscribe on schedulers.elastic, right? Something like that. So this will create new threads for every single use case, right? So if you're going to do something that blocks, it's very important that you do not do that work on the non-blocking thread pool, the default non-blocking event loop that Reactive provides, right? Because that is being used by all the different activities in the runtime. By default, that scheduler has one thread per core, and that's fine, right? So if you have 4 cores, you only have 4 threads, but it's no big deal because you're not blocking. And as long as you don't block, then you have plenty of speed. It's no problem, right? The problem is when you start to block. If you start doing non-reactive things, you need to make sure that you do that on a separate thread pool. Otherwise, you will stop other very important things from happening, right? So imagine you have 4 cores and you start using one of those threads to do blocking I/O or to do algorithmic stuff, something like that. If that happens, then you want to make sure that you don't do that on one of those threads, because you're not just blocking the thread for one request. If you have 4 threads, you're blocking 25% of all the requests in the system. That's not good, right? So it's very important that you do that. You say subscribe on, right? Or publish on. And there's some differences there, but basically it's very important. You can move work from one thread to another, one thread pool to another, right? So you can start it over here, do something blocking in the blocking thread pool, and then move back to the reactive thread pool when you're doing non-blocking work, okay? I hope that answers your question. Okay, so we now have our application. It's ready to go to production. The problem is we don't want to do, I don't want to tell you how to, I don't want to work with YAML and Docker files and all that. I think that's a waste of time. And frankly, we shouldn't be worrying about it, right? At Java applications, there's only so many ways to deploy an application, right? And so I can use build packs. Build packs transform your application source code into Docker images, into images that can run on any cloud. They were created by Heroku, and then the Spring team at Pivotal extended them, and we embraced them for Cloud Foundry. And now Pivotal and Heroku have donated them to the Cloud Native Computing Foundation. There's an integration of them. There's an implementation called Paketo, and so you can use it for all sorts of workloads, Java, of course, but also dozens of other languages and runtimes. And the idea is that we shouldn't reinvent this. How do you run a Java application? There's just only a few ways to do it. Why do we reinvent that recipe every single time? You can use Paketo by itself as a command line tool, or you can just use the built-in support in Spring Boot. So we have this here, Maven Spring Boot, Maven plugin. However, I don't want just a regular Java application in the JVM. What I want is a GraalVM native image. Now, GraalVM is an OpenJDK distribution that has some extra accessories that are very nice. One of the things that it has is the native image builder. The native image builder takes your application, analyzes it at compile time, it determines which classes you are using, and then it removes every other class that it cannot see being used directly. So it gets rid of everything on the class path except for your code. It gets rid of the JDK, all the stuff that you're not using in the JDK and the JRE. It gets rid of all the other libraries on the class path. And then it turns the code that it has left into an x86 or machine architecture specific binary. The problem is that Java is very, very dynamic, right? Java is a huge ecosystem, and it's not like C++. It has dynamic behavior. And so it can do things that you can't do in C++, like reflection, like proxies, like serialization. You can serialize Java objects, like JNI, right? It can do lots of stuff that's very hard for GraalVM to see. It doesn't understand at static analysis. So you have to provide configuration to tell it, hey, I'm using this class. Please don't throw it away, right? Even though you don't see it being used by the compiler at compile time, at runtime, I'll be using this. And so we built a project called Spring Native. Spring Native is experimental, but it provides the ability to tell GraalVM, it provides configuration for GraalVM so that it knows about all the things that Spring applications might do, because Spring pulls together this whole ecosystem. We are at the center of so many different other use cases, and so people use Spring and Hibernate, they use Spring and Netty and Apache Tomcat and all these other libraries, all throughout the ecosystem. And so we want to make it as easy as possible for people to take all of that and turn it into native images. Our goal with Spring Native is that you can take your existing Spring Boot application and convert it into a native image. You don't have to rewrite anything or throw away anything or anything like that. And so, obviously there's, 20 plus years of people writing Spring apps. It would be nice if all that could benefit from GraalVM. So Spring Native is on the class path here. It's experimental. I think the goal, at the very least, is to get it into Spring Framework 6, and then Spring Boot 3. But we also, I hope that they will also release a GA version of this as well. So I'm going to use the build pack support. I'm going to say Maven clean package Spring Boot build image, and that's going to create a Docker image in the background. Okay, it's going to create a Docker image. Oops, what happened there? Oh yeah, that's that. It's going to create a Docker image in the background, and it's going to run GraalVM inside that Docker image. I don't have to download GraalVM. And so that works in the background. It's going to create a Linux container. I can then deploy that container wherever I want. But remember, this will take several minutes. So while that's doing that, let's go create a new service. And this time, I want to create a service called the order service. And I'm not going to use HTTP this time. I'll use RSocket. RSocket is a reactive web protocol. It's an open protocol that was created by engineers at Facebook and at Netflix. Okay. And it's designed to solve some of the big limitations of HTTP and gRPC and things like that. It's trying to provide a natively reactive wire protocol that people can use that has the concepts of reactive programming, including back pressure, in the network protocol itself. And so it's very, very efficient, very, very fast, and it's very flexible. It supports lots of different message exchange patterns. So fire and forget, bidirectional, request response, streaming, etc. And in RSocket, you don't have client server. When one side connects to the other, they stay connected, and they are no longer client or server. They are requester responder. The server can ask questions of the client. The client can ask questions of the server. They are both equal in that way. They can have a conversation, and the server can ask the question first. So the client connects to the server. Then the server says, okay, now give me all the data you have about this, this, and this, and this. It doesn't need to be that the client asks a question first and then the server responds, right? Okay, so we're going to build a very simple order service using RSocket. I'm using Java this time. I made the mistake of accidentally using Kotlin last time, but it's fine. So we're going to use, 8181. We're going to create an RSocket controller, class order RSocket controller. And this RSocket controller, I'm not going to bother with a database. I'll just create a constructor here, and we'll just create a little in-memory database of order data. Now, order data is like you have customers, and I want order data as well. So map integer collection of order. And of course, the order is an object that represents the ID and the customer ID. Okay. So put that down here. Okay, so there's this. And for var customer ID, I'm just going to create some hard-coded data. You could talk to R2DBC, you could do whatever you wanted. But for me, I'm just going to create some synthetic data here. Var list of orders equals new array list order. Okay, and then I'm going to create some data there. I'm going to say var order ID equals 1, order ID is less than or equal to, let's say, math.random times 100. Order ID. And here I'm going to add the data. I'm going to say list of orders, add new order. And I'm going to give it the order ID and the customer ID. Voila. Okay, so we're going to say this.bb.put customer ID, list of orders, etc. Okay, so there's my random data. And now we're going to create an RSocket endpoint message mapping. So the URL is kind of like a path for a URL for HTTP. It's a destination. And here I'm going to return a reactive stream of order data for a particular customer ID, right? Integer customer ID. And the reason that this is a separate microservice, of course, is because the order data will live even if you delete the customer data, because you need the order data for revenue recognition purposes, or that kind of thing. Maybe it doesn't matter. So return flux.from iterable list, right? Good. There's our reactive stream. Let's go ahead and start this one up. And so we're using HTTP in the customer service, Perl HTTP localhost. Sorry, we're using HTTP for the reactive service, for the customer service. Let's use RSocket and RSC for this one, right? So TCP, whoops, wrong one. TCP, okay, localhost 8181. Route is orders.to, and the interaction model that we're using is streaming, right? So there's the stream data, etc. Okay, so now we have this. Let's go check on this. Is this almost done? Almost there. It's still compiling. This takes a long time. GraalVM is very, very slow because remember, it's not compiling just your source code. It's compiling everything on the class path as well. So okay, we've got an RSocket service. We'll soon have a customer service. Let's now build one more service. We'll go back to start.spring.io. We're going to build a gateway. Here, we're going to use the reactive web. We're going to use Lombok. We're going to use RSocket. We're going to use the what else do we want to use? Gateway, Spring Cloud Gateway. So this is an edge service. It's going to sit there at the edge of the architecture, in your architecture. And here is, this is a great use of reactive programming because it's going to allow us to accept requests from the outside, to transform them, to act on them, and then to send them to the downstream service. An edge service is the gateway into your system. And so it's a great place to ensure a consistent and quality level of service by centrally changing things, by acting on all the streams of data. So you can do things like routing, security, authentication, compression, all that kind of stuff that's great here at the gateway level. And to do this, we're going to create a gateway application that does two things. First, we're going to use an API gateway, and we're going to use a project called Spring Cloud Gateway. Okay, so Spring Cloud Gateway, route locator builder, and I'm going to create some routes. Turn. Good. I'm going to create a route that matches incoming requests that are going to this edge service. So this is a server that will run on a particular port. Let's say it's port 9999. It's going to go to this /path proxy, and maybe the request will have a host header. So host has to be wildcard.spring.io. Then we're going to send it to a URL. Now I want to send it to the customer service like this. The problem, of course, is that we can't send it to that service because we have to change the path, right? The path is going to be proxy, so we can use a filter. And we can configure as many filters as you want, but one that I'm going to use is to change the path in the filter. So that's one option. Okay. The other thing I want to do is I want to add a response header, HTTP headers. Dot allow, now I can support cores, common object, cross origin request scripting, that kind of thing. But there's other headers here as well. You can do a rate limiter. You can do you can change the body of the request or the response. You can do anything you want, really. There's circuit breakers, there's retries, there's all sorts of stuff that you can do here in a generic way. I'm using the Java JVM API. There's a Kotlin DSL as well that makes this even cleaner. But also you can use this in YAML. You can store this in configuration. That configuration could live in a config map or the Spring Cloud config server. You can then reload that configuration. So you can change the configuration outside of the application and then tell the application to refresh. You don't have to take the application down. You don't have to restart it. You can reload that configuration. So there's some very interesting opportunities here. One thing that people might use is we have a thing called Spring Cloud Gateway for Kubernetes. It's not open source. It's a product. It costs money, but it's also a Kubernetes distribution of this. So now instead of just using YAML in configuration, you can actually have an ingress controller powered by Spring Cloud Gateway, and that also sets up routes for each microservice. The YAML, the CRDs for each gateway route, they live with your microservice. They're not central like with Apogee or something like that. Okay, so here's my little application. Let's see if that works. And this is finished, by the way, over here, my Docker image. So let's run it, okay? Docker run port 8080, 8080. Okay, so it's gonna kick off. Whoa, oh, because I'm streaming, that's right. It's much slower because I'm streaming right now. It starts up in 0.2 seconds, so 1/5 of a second. Let me see what, I'm gonna kill this. Whatever. Normally it'll get down to about 0.1 seconds or something like that. And that includes an embedded database. Remember, I'm starting the database in the container. So there's my application on port 8080, local 8080 customers. So now we've got the gateway, the RSocket service, and the customer service. Let's go back to our gateway code, and let's see if that works. So I want to go here, curl, HTTP, localhost, 9999/proxy. I'm going to do -v. This will fail, right? It fails because there's no host header, right? So now host hello.spring.io. And there you go. There's HTTP 200, and there's the JSON that comes back out of it, right? So now we have all of this data here. And you can see that that gateway worked. It's very generic, but it works. Oh, and we also have this cross-cutting header, right? This is one thing you can do in an API gateway. Another thing you can do is to create an API adapter. So class CRM client, and we create a reactive stream. I'm going to create this is going to be a client for the order and the customer service, okay? So let's see, private integer ID, private string name, private integer customer ID and ID. And we're going to make these clients of the downstream services. But remember, one of them is HTTP, the other one is RSocket. But it doesn't matter because reactive programming is very good for composition, for service orchestration. We're going to do scatter, gather kinds of service orchestration here. So what I want to do is I want to build a client to give me all the orders for integer customer ID and return ID. I'm going to return all the customers as well. Okay. So we need to use a client to talk to those things. So we're going to use private final web client. This is the non-blocking HTTP client. And here's the RSocket requester. Okay. And this is like the RSocket client. But remember, in RSocket, there's no such thing as client or server. It's requester responder. They're peers. So we don't call it an RSocket client because it's not, right? Okay, so we need to build those two objects. So we're going to build them here. We're going to factory an RSocket requester. Okay. And remember, we connect at application startup time. We don't need to reconnect each time. That means that you don't have to recreate a new connection and do the handshake and the ACK and all that stuff. It's much faster to use RSocket for that reason, right? So then we're going to create the web client. And you can see that the strategy here is basically the same, right? You inject the builder, and then you create the instance that you want. Okay, so now let's actually build this implementation. Here, we're going to say this.http.get.uri, HTTP localhost 8080/customers. And the data that we expect to come back will be customer data. Okay, fine, that works. And what about the RSocket stuff? Well, we'll say RSocket.route orders.customer ID. I'm going to pass this in here. And then that data will be a stream of orders. Okay. Exchange to flux. Retrieve. Okay. So there's our two reactive streams. They're just streams. We can do whatever we want with them. But of course, things might fail. So like I said, one of the nice things about reactive APIs is you get these very consistent operators that you can use to describe how to handle failure, right? And so I can do a timeout. I can do all sorts of things here. I control how it does what it does, right? I can retry 10 times. I can retry and do a back off, with an exponential back off, that kind of thing. And these are operators that are part of Reactor. They're not part of RSocket or HTTP, so they work on both. Okay, so now I've got my two endpoints. Let's compose them and get a new endpoint. So I'm going to create a new view of the data called customer orders. Okay, and here I'm going to have a customer, and I'm going to have a list of all the orders. So I'm going to create a new view to compose the data and then hand them back to the client that way. So data orgs, no orgs. Okay, I'm going to create a new method here. Returns a publisher of customer orders. So get customer orders. I say give me all the customers. I'm going to map each customer, and I want to get the customer and all the orders at the same time. So I'm going to store them in my memory, in the memory here, in the process, in a tuple. So I'll say mono.zip, and the thing on the left will be the customer, right? C. And the thing on the right will be the orders. So we'll say c.getID. I'm going to collect that as a list. So if I go here now, what I get is a, flat map. What I get is a tuple that has T1 is the customer and T2 is the list of orders. So now I can turn that into my aggregate type. Tuple.getT1, tuple.getT2. Okay, very easy to do. I'm doing this concurrently. There's no threading here. There's no phasers. There's no countdown latches, no semaphores, nothing like that. It's just very easy code to write, and yet it's also the most efficient code that you could write. And so now I want to create an HTTP endpoint to demonstrate that. I could use the REST controller style, but I quite like the functional reactive style as well. So here's what that looks like. You say route build get COs. You provide a new handler function. Server response body. Okay. So here's my CRM client. Get custom orders.class. And voila, there's the entire thing. And this is different from the REST controller style, but they're both equal. You can use them both in the same app. That's the entire REST endpoint right there. It's just a one line, and it's a fluid DSL, so I can add other endpoints here. I can do it dynamically. I can have for loop, if, else, whatever. Oh, sorry, I gotta get rid of that. Okay. Perl HTTP localhost 9999/COs. There you go. So there's my customer data. You can see I've got the customer ID 8, Stefan, and there's the order data for each one with a customer ID. All right, my friends, we've looked at a bunch of things here that I hope will help you better prepare to write software intended for production. We looked at all the different things you can do, from liveness probes and readiness probes and observability and build packs and Paketo, and we looked at config maps, and we looked at a lot of different things you can do in Kubernetes. We also looked at observability with the Spring Boot actuator. We briefly looked at things like micrometer. We looked at reactive programming with R2DBC for data access and Spring Webflux for web programming. And then we looked at how to build a Docker image that uses Spring Native to create native images intended for a production environment. The native image starts up much faster and has a very, very small footprint, tens of megabytes, not hundreds or thousands, right? It's very, 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 very small. So you can deploy many of them and still cost less than deploying one JVM application. I believe that this will be a very useful thing for a lot of Kubernetes environments as well. And then we looked at different patterns that you can use to build services that handle failure correctly, that are efficient, that don't waste threads. I want to thank you so much for your time. Obrigado. I hope you're all healthy, happy, and safe, and I'm happy to answer questions if there are any.
Hello, everybody. That's the moment to fire your questions. And by the way, thank you, Josh. That was an amazing presentation.
Thank you.
And hopefully read your book soon.
Appreciate it. Yeah.
The new one, yes. So give once, give twice. No further question, Josh. That was amazing to see you here. And everybody, don't forget to follow us on Twitter and subscribe in our channel. So
yeah, absolutely.
Bye-bye.
Thanks.